Work and energy. Work is represented by W and is defined as F cosine theta times S. F is the force, S is the displacement, and theta is the angle between F and S. And this equation is valid for a constant force only. And in this diagram you can see the force F makes an angle theta with the direction of displacement S. So that's the theta in the formula. And the units of the work is Newton meters or joules. So these are two simple examples to show how to find the work. In the first example, we have a 16 Newton force makes 30-degree angle with the horizontal, and the displacement S is 20 meters. So force is 16, the angle is 30, so cosine 30 times 20, and it gives us 277 joules. And in the second example, the angle is 90, so cosine 90 is 0, so the work becomes 0. In general, work can be positive, negative, or 0. That depends on the angle. When the angle is less than 90, the work is positive. When the angle is 90, it becomes 0. If it's greater than 90, it can be negative work. The third example is work done by gravity. An object is initially at height y1 and final height is y2. The displacement S is in the upward direction, weight mg pointed downward. So the angle theta is 180 degrees. The height is basically y2 minus y1. Force is mg. Using the equation W equals F cosine theta times S, we have mg times cosine 180 times y2 minus y1. Cosine 180 is minus 1, so we get minus mg y2 minus y1. So the work is equal to negative mgh. We can always use this as a formula to find the work done by gravity is negative mgh. If h is positive, that means when there is an increase in the height, the work becomes negative. But if h is negative, that means when there is a decrease in the height, work becomes positive. Work energy theorem. So this is a very useful theorem. Kinetic energy is defined as 1/2 mv squared. M is the mass, V is the speed, and it's measured in joules because it's a form of energy. Work can be negative, but kinetic energy cannot be negative. It's always positive or 0 depending on V. So the work energy theorem tells us that work done is equal to the change in kinetic energy. So we can write the work W equals to 1/2 m V final squared minus 1/2 m V initial squared. That's the change in kinetic energy. Let's go over an example. The speed of a car increased from 20 meters per second to 36 meters per second. How much work has been done on the car by the engine? The mass of the car is 1200 kilograms. Ignore the work done by friction. So at this point we ignore the friction. We can use the work energy theorem. Work equals to delta KE, which is 1/2 m times V final squared minus V initial squared. So that's 1/2 times 1200 times 36 squared minus 20 squared. So that becomes 537,600 joules. So that's 537.6 kilojoules. This is the second example. It says a block of mass 8 kilogram is pulled by a 30 Newton force. The friction force on the block is 12 newtons. Assume that the block starts from rest and its displacement is 80 meters. Question A, find the work done by the applied force. Find the work done by the friction force. what is the final speed of the block? The values given in the question are mass equals 8 kilograms, the applied force equals to 30 newtons, and the friction force is 12 newtons. The displacement is 80 meters. To find the work done by the applied force, we use the same formula, F cosine theta times S. Now the applied force is 30 newtons. Theta is 0 because the applied force and the displacement are in the same direction. So it's cosine 0 times 80, which is 2400 joules. To find the work done by the friction force, we need to use the friction force times cosine 180, because the friction force and the displacement are in opposite directions. So the angle is 180 times the displacement 80. This gives us negative 960 joules. Then to find the final speed of the block, we can use the work energy theorem. Work is equal to 1/2 m times v final squared minus 1/2 m times v initial squared. So that equals to 1/2 times 8 times v final squared. The second term is 0 because v initial is 0. Now in this case, the work is the total work, which is this 2400 minus the 960. That's equal to 4 times v final squared. So v final squared equals to 360. V final is approximately 19 meters per second. Now let's go back to the forces. We have discussed forces before under Newton's laws, but now we're going to look at them differently. Let's try to understand what a conservative force is. There are two types of forces in nature, conservative forces and non-conservative forces. The difference between the two is that when the work done on an object is independent of the path, then the force is called a conservative force. For example, if we move an object from point A to point B, taking two different paths, path 1 and path 2, but the work is the same regardless of the path you take. So if that's the case, then we say the force is a conservative force. A good example would be gravity. If you do work against gravity, the work is always independent of the path. It only depends on the difference of the two heights. These are some examples for conservative and non-conservative forces. The conservative forces are gravitational force, spring force, electric force. Not all electric forces are conservative though. The induced electric forces are not conservative, but static electric forces are conservative. The magnetic force. The non-conservative forces are friction, tension, and the normal force. Potential energy. Potential energy is defined as the work done against a conservative force. Now we learn how to find the work if you do work against a conservative force. For example, against gravity, then we say that energy is a potential energy, because when you do work against gravity, that energy is stored in that object and you can use it later. So we call it the potential energy. And potential energy is also measured in joules. The best example is gravitational potential energy. Since it's the work done against a conservative force, the change in gravitational potential energy is the negative of work. But we previously found that work is negative mgh. So negative times negative is mgh. So the change in the potential energy is mgh. Normally we represent the potential energy as a change, but the convention is we use the potential energy at the ground level is 0. So we measure everything relative to the ground level. Since ground level is 0, the change in potential energy sometimes equal to the potential energy, because the initial potential energy is 0 at the ground level. Now we can use the work energy theorem and the definition of the potential energy to show that the energy is conserved. This is what we had before. This is work energy theorem. And then we also know that work is equal to negative times the change in the potential energy. If we use the two equations, we can say this delta KE is equal to negative delta PE. That means delta PE plus delta KE equals to 0. That means change of PE plus KE equals to 0. So if the change is 0, that means there is no change in this quantity. That means PE plus KE must be a constant. This is what we call the conservation of mechanical energy. But this quantity, PE plus KE, is called the mechanical energy of the system. And we say the mechanical energy is conserved and normally represented this way. E final is equal to E initial. This example shows how the conservation of energy used in problems. There is a block, 4 kilogram block, sliding down a slope. Initially the block was at rest. So the question is, find the speed of the block, assuming the surface is smooth, assuming that the friction force is 8 newtons at the bottom of the slope. So two questions. First, we assume that this is a frictionless surface, and then what would be the speed at the bottom of the slope? And then we consider that there is a constant friction force of 8 newtons, and then in that situation, what would be the final speed of the block? To answer the first question, it's a smooth surface. There are no non-conservative forces, like no friction forces. So we can use the conservation of mechanical energy, or E initial is equal to E final. Initially, the block is at rest, so the only energy it has is mgh, which is the potential energy. But finally, the height is 0, so there is no potential energy, but it has the kinetic energy, which is 1/2 mv squared. M cancels, then v squared equals to 2gh. So v is equal to square root of 2gh. By plugging the values, we can find that v equals 7.67 meters per second. Part B, now there is a 8 Newton friction force. So we cannot use conservation of energy or conservation of mechanical energy. Instead of using that, we will use the work. This is what we can use. We can find the work, total work, which is the work done by conservative forces minus work done by non-conservative forces. This is the work done by friction, because we lose that energy, so you have to subtract that, and that becomes the total work. But that total work is equal to change in the kinetic energy. So work done by the conservative forces is simply negative mgh. So negative 4 times 9.8, and h is negative 3 in this case, because the block is moving downward. So the total work under the conservative forces is 117.6. The work done by non-conservative forces is friction force times the displacement. So it's 8 newtons times the displacement is 6 meters. So we can find that because this angle is 30 degrees and this height is 3 meters. So sine 30 is equal to 3 divided by this distance x. So x would be 3 divided by sine 30, which is 6. So that's how I found this 6. So the work done by the non-conservative forces is 48 joules. The total work is 117.6 minus 48. It's 69.6 joules. Now we can use the work energy theorem, which gives us 69.6 equals to 1/2 mv squared. V is the final speed. So that's 1/2 times 4 times v squared. So v squared becomes 34.8. V equals 5.9 meters per second. Example 4. An object is sliding down a smooth track as shown above. The initial speed of the object is 8 meters per second. Find its speeds at A and B. So the initial speed is 8 meters per second, and initially the object was at 12 meters above the ground level. Point A is at the ground level, point B is 5 meters above the ground level. So we can use conservation of energy. E final equals E initial. E initial is equal to mgh0 plus 1 half mv0 squared, and that equals to m times gh0 plus v0 squared over 2. Same way we can write E final. E final equals to m times gh plus v squared over 2. By equating the two, m times gh0 plus v0 squared over 2 equals to m times gh plus v squared over 2. M cancels and it becomes gh0 plus v0 squared over 2 equals to gh plus v squared over 2. 9.8 times 12 plus 8 squared over 2 equals to 9.8 times 0 plus VA squared over 2. So this is 117.6 plus 32 equals to VA squared over 2. So VA becomes 17.3 meters per second. To find the speed at B, we use the conservation of energy again. mgh0 plus 1 half mv0 squared equals to mghb plus 1 half mvb squared. M cancels from the equation. Then gh0 plus v0 squared over 2 equals to ghb plus vb squared over 2. gh0 is 117.6, v0 squared over 2, that's 32, equals to 9.8 times 5 plus vb squared over 2. So 117.6 plus 32 minus 49 equals to vb squared over 2. 100.6 equals to vb squared over 2. So vb squared equals to 201.2. vb equals to 14.2 meters per second. The last section is power, P. Power is the rate of change of work. We can define the average power as the work divided by delta T. There are actually two equations. Average power equals to W over delta T, and also average power equals to force times cosine theta times the velocity. In this case, theta is the angle between force F and velocity v. The units of power are either joules per second or watts. This is an example. A 1200 kilogram elevator moves upward at a constant speed of 0.5 meters per second. Find the power required to maintain the speed. So in this situation, the elevator is moving at a constant speed. So the applied force is same as the weight. So that's equal to 1200 times 9.8, 11,760 newtons. The angle is 0 because the velocity is upward, the force is upward, so the angle is 0. So that's equal to 11,760 times cosine 0 times 0.5. So the power is 5,880 joules per second. The car, initially at rest, accelerates to a speed of 30 meters per second. If the acceleration of the car is 1.5 meters per second squared, find the average power of the engine. Ignore frictional forces. Mass of the car is 1200 kilograms. We can use the work energy theorem. The work is equal to 1 half mv final squared minus 1 half mv initial squared. Since the initial velocity is 0, work is equal to 1 half times 1200 times 30 squared, that's 540,000 joules. To find the average power, we need time, T. We can find T using the equation V equals V0 plus AT. 30 equals to 0 plus 1.5 T. So T equals to 20 seconds. So the average power is equal to 540,000 divided by 20. So that's equal to 27,000 watts.